Good afternoon, everyone, and thank you for taking the time to attend this keynote. I am a principal at Molino Stewart, a natural hazard and environmental consultancy firm based in Parramatta. My background and interest, among other things, revolve around flood and tidal inundation risk assessment, with a particular focus on the vulnerability of the built environment. I have been in the industry for over 15 years now, pretty much divided equally between commercial consultancy in Italy, academic research at the University of Sydney, and then back to commercial consultancy at Molino Stewart. And despite my reasonable level of seniority and being 44 years old, I have been asked to publicly state that I am a member of the Young Floodplain Managers Australia group. And I suppose this was to send a message of hope for anyone who may think they are too old to join the YFMA. So today I am presenting a review of Australian models to predict direct flood damages to buildings. The scope of this presentation is to discuss the different ways in which building damage models can be created and how this determines their inherent limitations that, in my experience, are rarely acknowledged. I will then provide an overview of the options currently available in Australia, with a focus on only publicly available tools for assessing direct and tangible damages only, and I will focus only on the key publications issued after 2007. For anything before that, you can there's already a review from Kathy Barton done in 2003, which is available on the FMA website. So what are stage damage curves? Well, first of all, typically, a building damage assessment model for flooding takes the form of a stage damage curve. And this is a mathematical model which associates a flood demand parameter, in this case flood depth, to the predicted damage level for a given building type. And as you can see in this chart, the flood depth is represented on the horizontal axis, while the damage level on the vertical axis. The use of stage damage curves in floodplain management is recommended by the Australian Disaster Loss Assessment Guidelines, and it is particularly helpful to inform the cost-to-benefit analysis of flood risk reduction options. Depending on how the damage is expressed, stage damage curves can be deterministic or probabilistic. Deterministic curves, like the one shown on the left here, provide a definite damage level for any given depth. While this is straightforward and easy to use, the curve only shows the estimated mean damage to that type of building and does not acknowledge the inherent variability of a building damage response to flooding. That is, similar buildings affected by, say, 1 meter of depth will likely incur different damage levels. On the other end, and you have an example on the right, probabilistic curves encapsulate this variability by showing the probability that a given damage state will be reached or exceeded in response to a given flood demand depth in this case. So, for example, if you look at the blue dotted line on the right, that corresponds to a building which has a probability of about 60% to have a damage above $25,000 and 40% to have a damage between $10,000 and $25,000. Depending on the way in which they are developed, damage curves can be empirical or analytical. Empirical curves are built based on field observation of actual damages sustained in historical floods. During post-flood surveys, the peak flood depth at a given building is measured, usually by looking at the water marks on the building walls. And then the damage to that building is assessed and associated to that particular flood depth. This process is then repeated for ideally a large number of buildings and generates a cloud of points in a depth damage chart, like the one we see here, where each point represents damage caused by a particular water depth to a particular building. Stage damage curve is then obtained by fitting a curve to that cloud of points, and usually we have a log normal curve, which is S-shaped like the one here. On the other hand, analytical curves or synthetic curves are not obtained by fitting real damage observations, but as a result of a desktop analysis. The first step here is to generate a theoretical prototype representative of buildings in the study area. The damage to each component of this prototype is then assessed for a range of flow depth, which creates a depth damage relationship, which then becomes the stage damage curve for that particular building prototype. Now, what are the limitations of stage damage curves? The limitations are different depending if we're looking at empirical curves or analytical curves. So for empirical curves, well, these curves represent the mean damage for any given depth of the buildings that were surveyed to create that particular curve. The mean damage of this building sample would ideally be as close as possible to the mean damage of the whole population of buildings represented by that curve. The accuracy of a curve is then defined by the standard error of the mean, which is the ratio of the standard deviation of the true population of buildings to the square root of the sample size. In other words, a curve is more accurate if it is built using a large sample size and if the variability of the class of buildings it represents is small. What are then the causes or the sources of this variability in empirical curves? There are three main causes: variability of the building attributes, people behavior, and flood demand. So for example, a single-story masonry building affected by a depth of about 1 meter could have variable damage responses based on its other design attributes, such as floor area, contents value, or level of finishing, but could also have different damage levels if the building occupants were to take preparatory actions, such as moving valuable content away from the water or using sandbags or what have you. Finally, different damage levels for the same depth could be caused by different flow velocities or water density. And in other countries, there are even other factors considered, such as ice contact, which are known to be a driver of damage. So in order to address all of these variability sources, a stage damage curve would need to be created for each possible combination of these factors. But this is hardly practical. It is impossible, basically. So in most instances, we have curves only for a few building types. For example, we could have a curve for a single-story masonry building of a given dimension. All the remaining variability sources listed here are then not addressed by the curve and go to increase the error of the curve. And because this not addressed variability is very much location specific, empirical curves should ideally only be used in the same area where these were originally developed. In terms of analytical curves, the accuracy depends on similar factors. In particular, the specificity of the building prototype is one of these factors, and this can be increased by creating multiple prototypes for various combinations of building attributes. The loss assessment exercise is the second factor that contributes to the accuracy of these curves, and the accuracy is driven by if the loss assessment exercise considers the extent to which the building components can be protected by the building occupants or repaired, as well as factors such as post-flood inflation. So what types of stage damage curves have been developed in Australia? Well, if we organize these by type, like I did in this slide, we could immediately see that all Australian curves are deterministic. Broadly speaking, these are equally distributed between being empirical and analytical, with the former including, on average, older work. I've listed here work that goes back to the 70s, but as discussed, this keynote presentation will only address more recent publications. And the first one that I would like to talk about is the residential building assessment, damages assessment tool provided by the New South Wales government in 2007. This was released by the Department of Environmental and Climate Change, now DPI, and it's presented as in the form of an Excel calculator. This tool was originally created to harmonize the methods and assumptions for different floodplain risk management studies, so that the department could compare apples with apples when it came to providing government fundings to different councils. The tool, which includes an Excel calculator, is based, as I said, on a set of stage damage functions for 3 types of houses, but cannot be used for apartment blocks or non-residential properties. The stage damage curves are empirical and were built by Risk Frontiers using 361 insurance claims from Hurricane Catherine in 1998 in the Northern Territory and the 1974 Brisbane floods. The model introduces several important factors that have not been previously looked at, including ways of compensating for damage occurred at different times based on the average weekly earnings, or a location where the cost to repair buildings is different. The guidelines openly acknowledge that the model has limitations and do clarify that this should only be used until better data is available. Now, the limitations are several and include the fact that the model is empirical, but it is not based on damage to typical New South Wales buildings, and that is based on insurance claims that are now 20 to 30 years old. Yes, values can be adjusted in time using the average weekly earnings, but the authors note that this would still significantly underestimate contents damage. The curves are also linear, whereas most recent models use log normal curves, and they seem to use a threshold of alpha meter to differentiate between high-rise and low-rise houses, which may result in a bit of inaccuracies when the flow depth is slightly above or below the floor level. Another significant contributor to Australian stage damage curves is Geoscience Australia, that has been continuously publishing and updating curves since the 2011 Brisbane floods. In 2012, GA published a set of curves for 11 typical Brisbane residential buildings. The prototype of these buildings had been created by surveying over 800 buildings in the area, and 10 different flood depths were used to create the curves. Separate curves were created for building fabric and contents, and for insured versus non-insured, uninsured buildings, to try and consider the effect of people's preparatory behavior. This was, in my opinion, an excellent analytical work with the high specificity of the building prototypes because of the high number of observations and the high number of building classes. The 2012 curves from Geoscience Australia were then validated against empirical data, against real damage observations in 2017, still by Geoscience Australia. The data was collected via postal surveys of over 1,000 addresses, and it was created and was used to create empirical curves for 6 of the 11 building classes of the 2012 curves. Given the large sample and the high number of classes, it is reasonable to assume that these empirical curves were fairly accurate. Results of the validation, however, showed moderate to significant error for insured and uninsured buildings, respectively. 2 examples of this error are shown here for building fabric only. The red line represents the 2012 analytical curve, and the blue line is based on actual damage observations. Importantly, the authors of this study found no significant correlation between depth of flooding and contents damage, which I find extremely interesting because it goes to say how variable the value and replacement cost of building contents can be and how difficult it is to predict this, the damage to this part of buildings with a model. More analytical work from Geoscience Australia was undertaken in 2013 in Sydney, where Tariq Maxkood developed 7 additional analytical curves for typical New South Wales building types, only for building fabric, but the study included also non-residential buildings for the first time since after unflood. However, to my knowledge, this work was never validated. Another significant piece of work is contained in this NCARF report about the 2011 Brisbane floods. Here, the authors adjusted the 2012 Geoscience Australia curves with empirical data from a large sample of insurance claims for buildings in the Brisbane area. Importantly, insurance claims were adjusted for factors such as post-flood inflation and underinsurance. 4 so-called semi-empirical stage damage curves were obtained for typical Brisbane residential buildings, aggregating damage to fabric and contents. The final 4 curves, which are shown here on the left, were then validated against an independent database from Queensland Fire and Rescue. Although the database had only qualitative damage descriptors and some inaccuracies in the reported flood depth, the curves from Mason et al. Performed reasonably well, with only a moderate overestimate of the damages as shown in the figure on the right. Another example that I would like to talk about is the work by Nafari et al., published in 2016. This work was undertaken by the University of Melbourne and the United States Corps of Engineers. And this is the only example of stage damage curves entirely represented by a single mathematical function, which you can see here on the right, in which 2 parameters must be entered each time using empirical damage observation or expert judgment to obtain curves for specific building types. As such, there is virtually no limit to the number of curves that can be created, but they require ideally empirical observation of damage. The model was developed for damages to fabric only, so no contents, for residential and commercial buildings, the former of which was validated in Maranoa Council, showing reasonably good performance. And the last study that I would like to discuss is the Brisbane River Strategic Floodplain Management Plan, undertaken by BMT in 2018. As part of this work, BMT developed analytical curves for residential and commercial properties in Brisbane. The residential curves were developed for 6 typical residential building types, and the building model or prototype that was used to create the analytical curves was based on a survey of 66 residential properties from Brisbane and 20 properties from Mackay. And then the curve were built using a expert judgment from a loss assessor at different flood depth. Analytical commercial curves were developed for 30 surveyed local properties, and then these curves were used to update the annual set of commercial curves. The authors do say that the curves were validated against some data provided by the Insurance Council of Australia, and that specifically was claims for 51 properties. But the authors do say that there was quite a high level of uncertainty associated with this ICA data because a lot of these properties had changed through time. Nevertheless, the validation exercise did not show any significant bias of the curves developed by BMT. So in my opinion, this is a significant work. It generated a comprehensive set of analytical curves for buildings that the authors define locally representative in the Brisbane area. However, because the building prototypes were generated based on a local survey, so they're locally representative, the extent to which these prototypes are representative of other building stocks in Australia should, in my opinion, be further investigated. And I was pleased to hear that this is being done in Rhys Thompson's presentation yesterday. So concluding, in Australia, the publicly available approaches are rather fragmented. There is no one-size-fits-all option. There's no probabilistic models at all. There are insufficient or outdated options for non-residential buildings, except just from those from the Brisbane flood study. Only 3 residential models were validated against real data, and they showed variable results. In some cases reasonably good. But there is limited capability to consider damages to building contents, which is very important where velocity is low. And there are limited options to consider flow velocity or duration in addition to flow depth, which is a problem particularly where flow velocity is high. In most cases, stage damage curves were developed for a small number of building classes, which means that these curves have low specificity and which in turn means that the error associated with these curves is greater. So this may be okay if the curves are used on large samples of buildings, for example, overall floodplain, because the deviations from the mean would sort of compensate. But this is often not the case, especially when we need to assess the benefits of flood modification options in medium to small catchments. I've seen options that would provide benefits only to 3 or 4 buildings in some cases. So in these particular cases, we are possibly dealing with quite a significant error on the benefit to cost analysis, and which reinforces the importance of undertaking sensitivity analysis. But on the other hand, we don't know what's the variability associated with the stage damage curves, which would be very helpful to sort of pick a suitable range in the sensitivity analysis. In terms of recommendations, I think that better empirical data is still a priority. Deterministic models in the future, in my opinion, should try and quantify and show the variability associated to the curve. Research should try and explore probabilistic options, not just deterministic models, because in that way the variability of the models would be automatically addressed. And end users should be aware of the limitations of stage damage curves, especially when these are used for a small group of buildings. And finally, obviously, more work is needed on damage to building contents, damage to non-residential buildings, and on the effects of other flood demand parameters in addition to flood depth. Thank you very much for your attention, and I'm happy to take any questions.